Time we stopped at the PN junction. I think we discussed in reasonable amount of detail what's happening with the holes from a diffusion perspective and drift current perspective, right? So let me summarize that a little bit here. So we said that we have majority carriers, which are holes, diffusing from the holes, from the p-type material to the n-type material. As soon as they cross the junction, they find free electrons. They recombine with the free electrons. They create a region without free electrons. So it's called the depletion region on the n side, right? And since this region is free of free electrons, the reason there were free electrons was because we had donors in there. These donors had positive bound charges. So the free electrons combined with the holes, we were left with the positive bound charges. Similar thing here, but on the negative side, right? This we said creates electric field, and hence, if there's an electric field that between any 2 points in this region, or between the depletion region, there's a voltage. This voltage is called the barrier voltage. This voltage was developed due to what? It was developed due to the diffusion process. It also helped, it was developed due to the diffusion process, so created ID. Right? Holes move this way, electrons move this way, and the current direction associated with the holes is in the same direction. Current direction associated with the electrons is in the opposite direction. So we ended up with diffusion current in this direction. Okay? And then we said that, okay, now that we have this electric field set up,
does it go from positive to negative? Oh yeah, it does. I saw the circles, I thought that was the negative charge.
This is, okay. And then we said that this electric field now is set up here, and then we have some minority charges, minority positive charges on the n side, and the n-type material, and we have minority negative charges on the p-type materials, on the p-type side. So what happens is, with these charges are moving around because of the heat, for the temperature, for example. When they are moving around because of the temperature, wow, they see this electric field. The electric field, we said that drift causes positive charges to move with the electric field. So it pushes these positive charges across the junction to the n side, and then pushes the negative charges across the junction to the pushes the positive charges across the junction to the p side. That pushes the minority negative charges from the p side across the junction to the n side. Right? And this is causing drift current in the opposite direction. Yes, sir.
Last time we said like a capacitor, right? It's acting like a capacitor. But this goes back and forth, right?
No, it doesn't go back.
It only goes from one direction to another.
An open circuit now. It's an open circuit, right?
Yeah.
We're open circuit. Diffusion current will always go this way, and drift current will always this way. And in open circuit, they're equal to each other.
Yeah, but you said that sometimes, like when this goes here, this will be like when it combines, there will be no room for free charge, and it will go back.
But that's what I said here. So we've set up these depletion region. The depletion region was set up because I freed this area from free electrons.
Yeah.
I freed it from free electrons. What was the source of the free electrons? The donor atoms that had an extra electron. These donor atoms that had an extra electron, with the electron that after the electron became free, there was a bound positive charge on the donor atom. This bound positive charge on the donor atom is no longer finding electrons to fill it. Before it was, in the n-type material, we put donor atoms, fine. Even though the electron became free, another electron from another donor atom maybe filled that hole.
Exactly.
Right? But now the p charges have combined with these free electrons, so I have a region of positive bound charge that has no other free electrons around.
And the potential difference.
And hence, here positive bound charges, here negative bound charges. If you have two regions with a difference in charge, and an insulating medium between them, it's like having a capacitor.
So basically, this graph is showing you when they're joining each other, that's the curve, and then when they're fully
Which graph?
This curve.
This one?
Yeah.
This is showing that the fact that there is a voltage here.
Yeah, but the voltage is changing because the holes are going to the electrons, right?
The voltage is being developed because of diffusion.
Yeah.
Because holes are moving
And
to the electron
after-
side,
after it's fully
electrons
diffused,
are moving
it
the.
becomes an open circuit
It's
with this voltage,
you,
right?
exactly. It's like an open circuit with this voltage. You have a
And-
voltage across
So
the barrier.
it will eventually be a horizontal line, the voltage, just like
What
a
do you
number.
mean? What do you mean
Like
horizontal line?
voltage starts from 0 and then it goes up. This is the curve of the diffusion, right? And
Okay.
then it stabilizes. When it stabilizes, that's the voltage of
Yeah.
the capacitor.
The voltage of across the capacitor. Yes. If you want to call this the voltage across the capacitor, it's the voltage across the capacitor or the voltage across the barrier.
Okay. The barrier.
So the capacitor is near the barrier, for example,
Okay.
right?
No.
So
Clear.
what happens if I somehow add more voltage to this?
If you add more voltage,
What am I doing?
you're,
I'm making.
you're making more holes diffuse to the electrons, or vice versa.
Am I helping the diffusion current or am I helping the drift current? If I make this voltage,
Diffusion.
I'm helping the diffusion. So diffusion current will increase if I remember this voltage was set up because of diffusion. So
Yeah.
you started diffusion, and then because of the diffusion a process happening, you uncovered bound positive charges.
Yeah, but
Right?
if you raise
So-
diffusion also,
I don't care about. I'm not raising diffusion. If you raise diffusion, if you raise
Yeah.
the diffusion, what happens?
the voltage will increase.
The voltage will increase to do what?
To
Is this voltage helping diffusion?
Oh,
Or
no,
opposing
it's
it.
opposing it.
It's
trying,
opposing
trying
it.
to stop it.
Exactly. So that's why if in open circuit condition, this is ID equals IS. If I now close the loop somehow, okay, by an external voltage source, and this external voltage source is such that its polarity helps E.
To become an open circuit.
If it helps E, exactly what I'm doing is I'm almost canceling diffusion current.
Yeah.
Right? If it helps E, I'm canceling diffusion current. I am increasing drift current. This is also called saturation current. That's why it's an S. Saturation current. Okay, it's also called drift current or saturation current. But remember, saturation current is due to what? Is it due to the majority charges or minority charges?
So the minority.
Minority charges. So it will have a fixed value. It will have a limit. You increase the voltage to a certain limit. You're going to help the saturation current to increase to a certain level. But again, there is a certain limited number of minority carriers in the N-type material and minority carriers in the P-type material, because you put a lot of donors and acceptors in these materials. So you decrease the amount of minority carriers in both. So if you help the electric field, you're opposing diffusion and you are increasing saturation current, but saturation current is already a small value. So it will level off to a certain value and that's it. How about you do the opposite? You find a way to create an external circuit that decreases this value of E. If you decrease the value of E, what happens?
You will increase diffusion.
I will
and
increase
you will
diffusion
decrease
and I will
saturation.
decrease saturation current.
If you increase diffusion, that means you decrease saturation. So
Sure.
They're like inverses.
Exactly. And if I increase diffusion current, and again, diffusion current is what's really causing the current to flow because it's
Okay.
the majority carriers,
The
right?
voltage will approach zero.
The
If you increase
it's
diffusion,
never going to approach zero. You will
the
you
more
will decrease
yeah,
this.
But the more you increase diffusion, the more it will become a short circuit.
The more it will. I mean, the more fine. The more this barrier voltage will decrease.
Yeah.
You agree that this is barrier voltage in steady state open circuit conditions.
Right.
We found a way to increase it and we found a way to decrease it. It will never be zero. It will never be zero, but it will have some value. You will still have some diffusion happening, right? And even when your IS has increased, you will still have some small value of diffusion. But the total value of current is the difference between them. So if there's a small value of diffusion current, larger value of saturation current, so the sum is what? The saturation current. So this is small, ID. This is large, IS.
IS is
So the current will be
Okay,
saturation
so-
current in the same direction as IS. This is the I is equal to IS minus ID. Right? So the total will be saturation current. The total will be due to the difference between the diffusion and saturation current, and will be in the same direction as the saturation current. How about in the opposite? But remember, IS is already a small value because it's due to the minority charge carriers, and it makes sense because in reverse. So in the reverse condition, in the reverse blocking condition of the diode, this is exactly what's happening. I don't want current to flow. I want the diode to block. So it's not going to be an open circuit. It's going to be something close to an open circuit. It will only allow a small value of current to flow due to the minority charge carrier,
Just like also our amplifiers.
which is very nice. It's like what?
Like our amplifiers, I don't want too much like voltage to go in.
I don't want too much current to flow from my sensor in that case.
Yeah, exactly. So we
Right?
don't mess up with the signal.
Sure, but this is a little different. This is a different.
What's the difference?
The objective. Think of a switch. Think of a switch, right?
Okay.
You would like to. Do we have any electronic? Do you know of any electronic representation of a switch now today?
A transistor.
A transistor is we didn't study that yet. I'm saying,
Just the
this is exactly what we're building
the
up towards,
computer,
right?
The computer. When you turn it on, you turn it off.
That's a mechanical switch. I'm talking about the electronic representation.
Electronic representation.
Yeah, I want something.
Transistor, as you said.
Sure, but we didn't study that yet. So I'm building towards the transistor now.
Oh,
This is
so
like a small.
semiconductors are the-
Yeah, this is like a building block of the transistor. The PN junction is like a building block of the transistor. This is a way to be able to make current flow in one direction and not
Okay.
the other too much, right? I cannot eliminate current to flow.
Oh, okay. And the reason for that is because if they went at the same, if they went opposite at the same magnitude, they will cancel each other out.
No current to flow. But
No
that
current.
only happens in the open circuit condition. If I have a closed loop around it and I happen to be putting, for example, let me go to the other slide that explains it better. 1 second.
The current will always go from positive to negative.
Let me
And the opposing charge will always be very small.
rotate. 1 second.
That's why, yeah.
Okay, yeah, here. So these are the various conditions we're talking about, okay? So if I
What's
I'm
the
in the
difference
open
between
circuit
the-
condition.
The R and the F?
be forward and reverse,
Oh, okay.
right? So we said one is forward bias.
One-
Forward bias is when I'm actually helping the diffusion current.
So basically the positive
Reverse
is this way
bias
and
is
negative
when
this way.
I'm
So
blocking, yes, sir.
So when the positive goes straight to the N junction,
It's doing what?
current's not going to be.
It's doing what? Why is it? Okay. Remember, we have
Yeah,
built
it's like a plus and minus.
we have built an electric field this way. We have created an electric field this way, and this electric field causes the potential difference this way, right? What is this external voltage doing? This external voltage is helping build a larger electric field,
But it's
meaning a larger voltage difference.
yeah,
Meaning
less
this
saturation.
barrier being high, the barrier to diffusion being high.
So it's making less saturation.
Saturation? No, I mean
It's aiding-
it's aiding saturation current, but it's limiting diffusion current. Remember
If
that
you limit diffusion, that means you decrease voltage.
I decrease current.
You
This
decrease-
is that's fine, but and right now I'm adding an external effect. You decrease, fine. I mean, an open circuit, what you're saying is correct. Yes, if I limit diffusion, if diffusion is moving, the diffusion is happening. When diffusion happens, I create this depletion layer with uncovered charges, which creates a voltage and hence an electric field. In open circuit conditions, the diffusion current and saturation current balance themselves out, right? So that no current is flowing. They're equal to each other. There's no there is a level of voltage now that is acting as a barrier to diffusion current. So there is diffusion happening, but at a rate that is equal to the saturation current existing as well. So they are balancing each other out. Okay. Now I have external conditions. I'm adding something external to the circuit. Now if I add something external to the circuit, that helps the electric field. Right? This is helping. This is going to help the electric field because it's a voltage in positive in this direction, negative in this direction.
For VGSR, the longer side is the positive, right?
For the voltage source, the longer side is the positive, yes.
Yeah.
So I'm helping now the electric field by creating a voltage that is aiding this potential difference that I had in my depletion layer, right? So I'm helping the electric field. If I'm helping the electric field, then I'm opposing diffusion, right?
Yes, it's
I'm
going
opposing
to-
diffusion externally.
Yeah. So it's going from
Externally,
negative to
not. I'm helping do that by an external source,
positive. Yeah.
right? So
it's going from negative to positive, right?
negative to positive,
Yeah.
yes.
So basically, and also in the P and then it's going also from negative to positive.
I'm not sure what.
No, but
The electric field will not change directions.
I know it's
the-
always going from negative to positive, right?
It's
So
always
naturally-
from the cathode to the anode.
the
It's
anode,
called
yeah.
of the
So
diode.
naturally, if you add a voltage source
Yeah.
that is with the negative side, of course it will add more. So
Sure.
of course there will be bigger voltage.
Sure. So
But I was mixing between this and the open circuit condition. And the,
yeah. Open circuit. What happens is there is a
Yeah.
steady state balance. The steady state balance maintains a certain barrier. This is called. It's a barrier to diffusion current.
Yeah, so that's why
Right.
here it's V naught plus VG, and on the other one it's V naught minus VF.
Exactly. So V naught plus VR. VR is called the reverse bias voltage. This is the reverse bias condition. Reverse forward bias condition is a condition that you want the diode to conduct. You want the switch to close. When do you want this? If the switch closes, current will flow. The large current will flow.
Yeah.
If this switch has leakage, right? Then even when the switch is open, there will be a small value of current flowing. Right?
Full time.
It's like having a resistor. It's like representing the switch as a resistor with a very high value and a very small value.
Very small value.
If it's a very high value, it's like the switch is open. A very small value is like the switch is closed, right? So saturation current flow, or the current flowing in the direction from the N-type material to the P-type material, which means that the saturation current is greater than the diffusion current, is like having a resistor with high value representing the mechanical switch. Okay? And then physically what's happening is you are aiding or increasing the barrier voltage.
What is the use for this?
What is the use? Here, we just said I'm creating a switch.
I know it's a switch, but
Yeah.
what is the use for it?
I will show you.
Isn't a switch
Yeah.
better because it's either 0 or 1?
But the switch, you need Abdelaziz to sit down and push it. I cannot have 1 million Abdelaziz inside the processor. I have 2 billion processors, 2 billion transistors inside the
There's 7
processor.
billion, no?
Huh?
There's
7 billion? Okay, 7 billion
Yeah, but
transistors
it's a
inside
bit-
integrated circuit, right? So really we have to go to the electronics. We cannot.
And so that's basically like how, basically you're making the system plus a switch.
It's
without
like
it
that,
working.
exactly. This is like a switch, okay?
Okay.
This is now, is it controlled or uncontrolled? It's controlled by external circuit conditions, right?
And you can change the voltage that you give.
Sure, you can do that. But then next we will, in the transistors, we will develop a more complicated way to control it, basically.
Based on voltage and not on.
Voltage or current. Here I'm controlling it based on the external circuit power supply, right? But this power supply current is actually flowing through the device in both conditions, right? So it's having the control current being the same as the power supply current is not a nice thing. Because sometimes you actually want to control your power supply current. So how do you do that? Right? It's a catch-22 in that case. So, and that's where we will introduce transistors, right? But so this is called in power electronics or in electronic circuits, this is called an uncontrolled device. Right? It's an uncontrolled. It's controlled by uncontrolled, meaning it's controlled by external circuits, not controlled due to the physics, due to a internal stimulus, for example. Right? So do we agree that we aided the barrier voltage, meaning we limited diffusion more? If you limit diffusion is your majority carrier transfer, right?
Okay, so what we're trying to avoid is to limit diffusion.
You want to control diffusion. Diffusion is actually the mechanism that allows current to flow through your device, right? The majority carriers to flow through your device, right? You have some small minority carriers. They exist, okay? But they're not the reason why current's flowing through the device. They're a reason why a small value of current is flowing through the device. But if you want current to flow, if you want to control power supply current, if you want to put a resistor here or a light bulb here and make this light bulb light, right? This light bulb has to have a certain current flowing through it. Saturation current is in the order of this saturation current. The maximum value of saturation current in a typical device is in the nano to picoampere range. Actually, for small signal diodes, it's 10 to the minus 15 amps. This is saturation current, typical value of saturation current. So is this enough for you to light up a light bulb? No. Right? So saturation current is not what does it. Saturation current is actually what blocks the current from flowing. It's what prevents the device from conducting it. Right?
So saturation doesn't help when it comes to.
So drift is not helping the current flow. Drift is actually helping you control the device. So you're controlling the device by, here drift current was equal to the drift current was equal to the diffusion current. Nothing flows. Here, what happens? Drift current was higher than the diffusion current. Why was drift current higher? Because I've created a higher electric field due to the internal internal electric field that I had before, which was due to the barrier voltage. Now I have an additional voltage that is aiding the barrier voltage that's creating a higher electric field, and hence, if I have a higher electric field, I prevent higher diffusion from happening, and I have higher drift, right? So I have higher drift current, less diffusion current. The total current is the difference between them. Now the difference between them is, going to be more on the saturation side, right? The saturation current or drift current is higher than diffusion current. So current will flow in this direction, from negative to positive of the device, from the cathode to the anode. This is not the current that will actually be useful for you to transfer power, because, as we said, saturation current is in the order of 10 to the minus 15. I'm actually seeing only part of it flow through the device. Is this useful? No, it's not useful. So what's the other condition now? The other condition that we have is, of course, I flip the polarity of the voltage. So instead of increasing the barrier voltage, I add an external power supply to decrease this barrier voltage. So my barrier voltage was V0, right? I added an external power supply. I had an electric field that had this magnitude. I now added an external voltage source that added an electric field in the opposite direction. So the sum is an electric field that is smaller than what I had before. Smaller. That's why they drew this distance smaller than the original distance, smaller than this distance, just to give you a flavor of.
So this whole picture is just trying to show us how to increase diffusion and
how to either have no current flowing due to diffusion to the external circuit, or how to increase it, or how to decrease it.
What do you want to do?
and once you increase it.
Why do you want to increase? If you increase it, it's like having a switch that you closed. And again, we said that the switch can be represented as a variable resistor that has, at one side it has 1,000 mega ohm, 10 to the 10 to the 12 resistance, and on the other side it has 0.01 times 10 to the minus 12 resistance. Right? This is a very high value, a very small value. Okay, if I'm able to have diffusion current flowing, it's like I closed the switch. It's like I closed the switch. If I'm able to prevent diffusion current from flowing, it's like if I've opened the switch. Right? And how did I do that? By playing with this electric field. This electric field represents this barrier voltage. This barrier voltage had a steady state value V0. And we found ways to increase this barrier voltage and found ways to decrease this barrier voltage. How do you increase the barrier voltage? By adding an external voltage source connected, its positive terminal is connected to the N-type material. And then how do you decrease it? Adding an external voltage source where its positive terminal is connected to the P-type material. Okay, so this is open circuit, and this is called the reverse bias. And this is called forward bias. Okay? Do we see this? Okay. So if that's the case, we can sort of I skipped a bunch of stuff here.
It's actually 5.5 billion.
5.5 billion what?
The transistor count on the CPU is the strongest one now.
Billion?
5.5 billion.
We can look at that. I don't know what you're referring to. But anyway, so we talked about the barrier voltage. We know what it is at steady state. We're fine with that. At equilibrium, we said that the drift and diffusion currents become equal. We talked about this topic, and why is that happening? It's because you have diffusion happening, you get more electric field. Electric field stops diffusion and helps saturation, and then they balance each other out at open circuit. And we discussed how to play with them with this barrier voltage at using an external circuit. So ID equals IS when it's open circuit. And then this junction voltage is a value that is typically between 0.6 to 0.9 volts. Typically it's between 0.6 to 0.9 volts, and it depends on the thermal voltage. Remember, thermal voltage was the ratio of the diffusivity over the mobility of the charges. We talked about that 2 classes ago. It's a constant that is actually typically equal to 25 millivolts. It's the ability of the carriers to diffuse over the ability of the carriers to drift. Diffusion over drift. It's a constant. It's the constant that depends on temperature, because if the carriers are drifting, it's because they are minority carriers and they are drifting due to the electric field, right? So it's a constant that depends on temperature, and we will write its equation later in the text. We just talked about it as a constant before. But its constant depends on temperature, and it will have a value that's typically around 25 millivolts. So this will have a value of typically 25 millivolts, right? And it makes sense that this barrier now, voltage, depends on concentration of acceptors and the concentration of donors, right? So, and it has some temperature dependence as well, because it has some intrinsic carrier concentration as well in the equation, right? So
These are all given.
yeah, just telling you that this is what this barrier voltage equals from the physics. We did not derive it. We did not derive it, and we will not derive it here, right? I'm just saying, this barrier voltage. We said that this barrier voltage develops due to the diffusion happening, and then it helps also the drift happening. So there's a steady-state barrier voltage is due to both having acceptors, having donors, as well as having some intrinsic, properties of silicon, meaning the minority carrier is moving as well, right? So that's what this means here, and this will become a very important range of numbers. So this 0.6 to 0.9, this VO, this barrier voltage is 0.6 to 0.9 for devices, for silicon devices, especially low voltage silicon devices. For power devices, this changes a little bit, but for silicon devices, low power silicon devices, it's between this range. Typically, we will use 0.7. Right? What does this mean? It means that below 0.5, 0.6, 0.7, whatever, what's going to happen? Is the device, ideally, if the device going to conduct current? No, because there's a barrier voltage. I have to exceed that, right? Remember, the current is now my diffusion current. I want my diffusion current. Can I make actually the current is actually the difference between the diffusion and saturation. But saturation is so small, right? So that's why I neglect it and I just say diffusion really, mainly. So I would like this diffusion current to increase. For me to increase this diffusion current, I have to overcome the barrier, right? So I have to overcome this barrier voltage. So only when the device, I'm putting a voltage on the anode side of the diode that is greater than this range, will the device start conducting. So an ideal representation of the diode can look like this. This is current, and this is voltage across the diode. And as soon as I have voltage that is greater than 0.7, I conduct, right? And then what happens in the reverse?
Separate.
No, in the reverse meaning saturation current is more than diffusion current, right? In the reverse, I will always have saturation current, right? And the value of the saturation current will depend on the value of the electric field that I have, right? The more the electric field, the more the saturation current that I have. So I can draw something that looks like this. I exaggerated here because, of course, this is very small. This is, this has a peak value here, I equal to IS, equals 10 to the minus 15 amperes, for example, right? Very, very small, right? But this is how a diode, approximately works. The rest of the chapter spends a lot of time looking at more details of how this diode is operating. But this is simply how it works, okay? And we see this application of this 0.6 to 0.9 volts, right? And then, I will skip this section, but basically here what they're saying is that, remember we talked about the mobility and diffusivity of holes and electrons. Mobility and diffusivity of the electrons was higher than the mobility and diffusivity of the holes, right? So if I want a certain amount of current to flow, due to the majority carriers. If the majority carriers are electrons, they can move easily due to diffusion and drift. So the holes will move a little bit more difficult. The diffusion current is due to both moving, right? So I may need more holes on the P side to have the same contribution of charge movement due to the N side. So that's what this section is talking about. The percentage, they will talk about it here in detail. I will skip this section. I'm just asking you, I'm just letting you know why here this is bigger than this. And here they talk about this in more detail. I will skip this. I will just, I just want you to see why they did this. It's because of what the mobility and diffusivity being different here. But this section I will just skip this one. And they talk about the width of the depletion layer, etc., etc. So that stuff I will skip. There's some, this stuff I will skip. It's more device physics, and it's not. I mean, it's interesting, but we're not going to spend too much time. We spent enough time on device physics. So it's like, it's physics and chemistry together. That's what device physics is. Device construction is. If you like physics and chemistry together, you can. Very nice area to go into is device building the power devices or building devices. Materials for devices. Okay, and then we talked about this. We talked about forward bias operation, reverse bias operation, and open circuit operation of the diode. And the whole trick is, how do you control the barrier voltage? If you control the barrier, if you increase barrier voltage, that means you are blocking diffusion. The device is said to be in reverse blocking condition or reverse bias. If you are decreasing the barrier voltage, you are allowing more diffusion. The device is said to be in forward bias. It will depend on the external circuit that you're applying, right? So based on the external circuit, the diode will either be in forward bias or it will be in reverse bias. But there will always be a junction, and there will always be a junction voltage. This junction voltage is going to range between 0.5 and 0.9. Okay, there will always be. So in all conditions, they left this depletion layer. They showed the depletion layer, but different thicknesses, right? There's always a voltage. Here we have the uncovered charges. Remember the uncovered charges that are creating voltage difference? There will always be a voltage difference, but it will vary depending on, if your device is conducting or not conducting. Okay, so we talked about this. Then they talk about depletion layer and charges. I will skip that. This is, this is something we understand, that the actual current that's flowing through your circuit now is the difference between them, between the diffusion and drift currents. Okay, and then I will, in this section here, I will also skip quite a bit, but I will talk about something that's interesting. So, one thing I will relate to what we're going to be talking about next. It's a short chapter, yeah. No, we still have a lot to do. But here, one thing, because what we're gonna, I talked about this. Okay, after 0.5 or 0.6 volts, we said that the diode will start conducting current, right? After you exceed the barrier voltage, yeah. But is this an abrupt thing that's happening? It's not an abrupt thing that's happening. It's caused by what? It's caused by the fact that you are allowing more diffusion to happen when you decrease the barrier voltage, right? But when diffusion happens, what's happening when diffusion happens? The holes are moving to the N-type material. The majority carriers from the P-type are moving to the N-type material, right? Recombining with the free electrons and hence creating this depletion layer, etc., etc. So these holes that are moving from the P-type material to the N-type material, they are gonna, as soon as they cross the junction, they will see what? They will see the holes, right? They are the electrons, right? They are moving because of what? The changing concentration of holes, right? They see no holes on this side, so too much holes on this side, so they are moving due to the effect of difference in concentration. This difference in concentration happens to have an exponential sort of characteristic. Okay, as soon as you hit the N-type material, what is the theoretical concentration of majority hole carriers? Almost zero at the N side, right? About at the beginning of the P side, a lot of holes if I'm injecting from one side, right? So it's like an exponential function here. So since this concentration is like an exponential function, we will find that the current, so the concentration is like an exponential function. The current that was due to the diffusion current, due to the current that's due to such charges moving, if the charges are concentrated exponentially, and the current itself will depend on the concentration. The value of current, the magnitude of the current will depend on the concentration. So it's like you're multiplying a fixed number by this concentration. I mean, the movement of charges depends on the concentration, and the movement of charges is actually current, which means that the current also depends on the concentration, and hence the current will also have an exponential shape, right? So here we said that the charge distribution is sort of exponential. So if the charge distribution is sort of exponential, then the current distribution will also look something like the value of current flow due to this exponential concentration will be an exponential function as well. That's what I'm trying to show you from this section. Again, we will not go through and look at this in detail and look at the concentration on the p side, the n side, and the current densities. I'm just the moral of the story is that the p-type, in the majority carriers in the p region, are the holes, right? They move to the n side due to diffusion. When they move due to diffusion, they will of course gather here. They will be higher here than they will be here. Hence, the current due to the specific concentration will be dependent also on the concentration itself, since the movement of the charges is concentration dependent. Yeah. So we will find that the equation for current, since the equation, they derive the equation for current density. Since the equation for current density has this exponential, that is dependent on Vt, right? This Vt is something that depends on temperature as well and the material. So again, I will skip this stuff. And the outcome of this section is the fact that current will depend on, some fixed values due to the materials and the concentrations, and this will have an exponential shape. Okay? Yes? No? This exponential shape, if we look here,
Comes from the fact that it moves with the concentration.
yes, I mean because of the concentration, because the concentration is exponential due to diffusion. So again, remember, diffusion is what? Diffusion is the movement of charges or carriers from one side to the other due to the difference in concentration. So this is the definition. Diffusion is due to the difference in concentration. Right? So since diffusion is due to the difference in concentration, and hence diffusion current is also due to the difference in concentration. Right? So that's why the diffusion, so that's why the current that's going to flow through the diode, the majority, again, remember, the significant amount of current is due to diffusion, right? Saturation current is here. It's very small value. What the model we drew before was what? The model I drew before was this, and I drew here, and I drew here. We understood this. This was 0.7 volts, for example, and this was voltage across the diode, and this was current. This current I is the difference between diffusion and saturation current. We said saturation current is neglected when the diode is forward biased. And I drew something straight up like that. Is it really straight up like that? No. It actually rises exponentially like this. That's all I'm saying. Okay? That's all I'm saying, is that it rises exponentially this way. And we will find that also here, we will have something like this happening, but exponentially as well, right? So, but for now, they don't include that in the model at this point. They will include it later in the model. But does everybody see now the relationship between this and this? I mean, this I hope we understood. The red, I hope we understood. From
What's the 0 point?
what is what?
Like the number, the range, plus 1.
0 point, let's say 0.5 to 0.9, for example.
Then 0.7.
0.7, I took one of them. I took one. So it's starting here at 0.5.
I thought it's a fixed.
And this will have a slope actually. It's not straight up. will actually have a slope that's, between, here we have 0.9, for example, depending on the value of current, okay? One thing to note, okay? If you have a voltage, so this is now my diode. I will represent my diode now. I will draw it next. But this is now my diode's anode. This is my diode's cathode. Here I had the P-type material, I had the N-type material. Current is flowing in this direction, right?
Oh, so in order for it to go, there has to be a specific amount of voltage.
Exactly. Yes.
And that's what we've been doing.
Exactly. That's what I've been talking about, right? It's the barrier. You had a barrier. This barrier, you have to decrease the barrier by creating a forward bias condition. How do you create the forward bias condition? By adding an external source that puts a positive voltage here versus this node in the circuit. If you do that, you decrease the barrier voltage, allow diffusion to happen. So drift is small. I don't care.
And if you like change it, like
If you change it, you move into the negative here. You flip it, you move into the negative. What's going to happen? You're increasing the barrier to diffusion. And you're allowing drift to occur.
and
But
the
drift is due to minority carriers that are already a small amount. That's why this is limited to a small value, and it's called saturation current here.
and we don't want drift, we want diffusion.
We want both, because I would like to have a switch. My objective is to have a switch, to create a switch. So I want to be able to operate in this condition and this condition.
Oh, but if it's just on the drift, it's not. If it's
No, drift will not. It's an open circuit. This is drift.
okay,
This is what you get when you are supporting drift, and this is what you get when you are supporting diffusion, right? This is something like that, right? So this is like an open circuit, and this is closing the switch, right? So this is diffusion happening, right? So diffusion current, we said, like this is like the switch closing, but is this diffusion current infinite? Can you have an infinite diffusion current? You cannot, because theoretically, according to the model that we have here, this current can go all the way to infinity. But remember, this is a physical device. This is a physical device that has, it will burn, because now there's a power loss. Since you have current flowing, the model for this device when current is flowing looks like this. Actually, there's a voltage here. This is my new barrier voltage VF plus V naught. This is a voltage, right? That's opposing your current. Current is flowing in this direction. This is the current flowing here. This is this current flowing here, right? This current is flowing, and it will only flow if the voltage is greater than this voltage, right? So if I have a voltage source here, this voltage source that I have here, I put it here, right? And I put, let's say, a resistor here, right? If this voltage, and this we said is 0.7, for example, right? If this is 0.7, this has to be greater than 0.7 for current to flow in the circuit. Do you agree? This is a voltage source. This is another voltage source. If this is 1 volt, then what is the current through this resistor R? It's 1 minus 0.7 divided by R. Right? Yes? So it has to be greater than this voltage for current to flow. But what I'm saying is that this is not abrupt. There's no such thing as an abrupt change, right? This diffusion and drift is due to the fact that you have a number of charges in the depletion layer, and you're moving minority charges over, majority charges over to create this current. So I'm saying it's not abrupt, it's exponential. That's all I'm saying. Right? That's all I'm saying, is that this is not abrupt, it's exponential. Here I modeled it as abrupt. Abrupt change in circuit condition.
And it makes sense.
Okay?
Nothing happens so
Exactly. If this is 0.5, what's going to happen? If I look at this circuit, what's going to happen? What's the current flowing in this circuit? It's going to be 0.5 minus 0.7 divided by R. But this is only a fictitious thing, because this would flow in this circuit. But actually, physically, my diode here is limiting this current in the opposite direction to what? To this saturation current. So 0.5 minus 0.7 divided by R will not flow. What will flow is a maximum value of IS, which is almost 10 to the minus 15 amps. Zero, practically. Do you see how this diode functions?
No, but if the current will not flow, then
In the opposite direction?
yeah.
No, according to this model, it will not flow. At some point, you will break it. When do you break it? When you put too much reverse voltage. If you put too much reverse voltage, we will go into that next, but let's look at this now.
No, but this one will not flow yani, because of the value, and it's a small value.
No, it's not. It will not flow because what did you do? You put this device in reverse bias. In reverse bias, you were helping the electric field. You were creating a larger barrier voltage. You're creating a larger barrier voltage, preventing diffusion. But when you created a larger barrier voltage, you also allowed drift to happen. But this drift is small. So now your external circuit caused you to limit the current in the reverse direction to drift current. So it's like opening the switch.
No, but instead of 0.5, it was like 5.
5? Even, okay. No, if it's 5, then it's greater than 0.7.
Yeah. So if it's
No, if it's greater than 0.7 and in the positive direction, here, this is what this characteristic tells me. If I put a positive voltage across the diode, this is my diode voltage, VD. This is its positive, this is its negative. If I make this VD positive and greater than a certain value, I will start seeing the diffusion current taking over. And I can push, theoretically, infinite current to the device. But infinite current is a fictitious thing. You cannot have infinite current in a physical device. Because since this is current flowing through the device,
we want current to flow, right? Or we,
you want to create a device that will allow current to flow when you want it to flow, and it will block current from flowing when you want it to block current flowing. You want to create a switch, right? But a very ruggedly, a very poorly controlled switch because it depends on your external circuit conditions. You depend on your external circuit, which is the circuit that's providing the voltage at your anode and cathode, to control the switch being on or off. That's what you're depending on, right? Which is a switch. You still have a switch, but it's a switch that is not nicely controlled, okay? But do we see now how this is operating? Abdulaziz? I see that, but do you see how this is operating?
Yes.
Okay, so theoretically speaking, if I make this resistance a short circuit, right, and I make this source, 1 volt, then current should flow equal to 1 volt minus 0.7 divided by 0, so it's infinite current. So theoretically, this model will allow infinite current to flow. But, I cannot allow, this is a physical device. It's a diode that's a physical device, has a certain cross-sectional area. This certain cross-sectional area means a certain current density can flow. Beyond that, again, if you have current flowing and you have through a battery model, right? What does this mean? Power is equal to V times I. Right? Power loss in the device will be this 0.7 times the current I. So at some point, let's say I have a Zener diode, I have a diode datasheet, for example. This is a diode datasheet, a special diode, but it's called a Zener diode. But look at this one. It tells you that this has a 1 watt power dissipation. That's it, maximum. It only allows 1 watt power dissipation.
So that's the power, that's how you call it.
That's a power that you allow to dissipate. So if you have a 0.7 volt drop, this is current flowing through the diode. This is the diode this way. This is current flowing through the diode. Current flowing through the diode. This is I. This diode is in forward bias now. I'm able to forward bias it, so this voltage is 0.7 volts. So power is equal to 0.7 volts times I. They're saying that in the diode that I selected, this P is equal to 1 watt. So what do I get? How much current can I push through this?
1 over 0.7.
Exactly. 1 over 0.7 amps is the maximum I can push through this device.
Is that enough?
It depends on your circuit. There are diodes that are rated for higher power.
What about like for lighting the light bulb?
Lighting the light bulb, again, it will depend on the light bulb is what? 40 watts, for example, light bulb. So is this going to be enough? 40 watts is the light bulb, and then your voltage, your line voltage, let's say the line voltage in the US is 120 volts. Let's say it's 100 volts. Right? And then let's say it's DC for now. It's AC, and it's all fictitious, right? But power is equal to V times I. If V is 100 volts and power is 40 watts,
1 over 4.
then
1 over 40.
40 over 100, right? Current is 0.4 amps, right? So 0.4 amps is what you have flowing through.
The maximum that you can have flowing through.
The maximum that you can have, no, this is what you need to light the light bulb.
What
So
if
it's
I have more?
0.4 amps. This light bulb, if I find a light bulb that's 40 watts, and my voltage is 100 volts, then I need
Yeah.
a current of 0.4 amps.
At least a current of 0.4.
0.4, I mean, not at least. This is what your light bulb needs.
Is the LED like required?
LEDs are a lot less. So LEDs are a lot less.
That's why they're cheaper.
No,
It's not a matter
LEDs
of
are
cheaper
more
though.
expensive.
There are very expensive
No,
LEDs.
like cheap to maintain, like to use. Isn't that
No,
why
because the
they're
LEDs,
efficient?
the LEDs, they require. It's like the LED is a diode actually. The LED is a diode.
No,
So you just need to be able to overcome its forward bias voltage or this barrier voltage to be able to light it up.
I know one light bulb costs 3 riyal. An LED costs around 7 to 14 riyal.
Yes, but the LED light bulb is different because it's very okay.
Why
This
is
is
it more
semiconductor.
expensive?
No, it's semiconductor. The incandescent light bulbs. It's a resistance. The incandescent light bulb is nothing but a resistance.
Yeah.
Right? It's a resistance R, and you have this R current flowing through it, heat generated inside this light bulb. This thing will have a lifetime that's much less than a piece of silicon. This is a piece of silicon. The LED is nothing but a piece of silicon. Fine, it has a case here and it has some heat associated with the fact that it's lighting up, but at the end of the day,
Why can we make it a lot of colors? That's another question I have.
why can you make it a lot of colors?
Oh, is that?
That's device physics now.
Alright.
That's device physics.
It doesn't have to do with circuitry or no?
No. It's device
I
physics.
thought it had to do with like the amount of current.
Exactly, I thought that
I kind of
too.
thought.
But that's why. So it's device physics that is controlled by the circuit that you create. So they want you to create a circuit that creates different values of current for different values of intensity of the light bulb. So
So
I-
it is about color.
again, it's if you push more current through it, it's able to change its physical properties. Yes, maybe they have materials that when they heat up a little bit, they become red or blue. I don't know. I'm not a LED expert yet, but we can dig into it if you want. But basically, it's a diode.
We have 10 minutes. Oh,
Huh?
You have 10 minutes for this.
No, we can. I can spend. I mean, I can prepare a few nice slides about it. But for now, just let's bear with me so we can move forward a little bit here. So, but is everybody now okay with this?
Yeah.
Do we see that there is an ideal? Okay, so remember, now we discussed 3 models of the diodes. There's one that is ideal. Ideal meaning anytime you put it in reverse bias, I will not conduct any current. I'm here at 0. And anytime that I have the diode in forward bias, I will ignore this barrier region, barrier voltage, and I will have as much current as possible. This current is limited. You have to limit it by your external circuit, otherwise you will bypass the power dissipation limit of the device. So this current theoretically can go to infinity, but that's why you have to make sure that your circuit limits that current. If your circuit doesn't limit that current and you put a short circuit across it, the diode is happy, it will conduct. But it will conduct it not knowing it's getting hot and burnt, right? But that's why you design your circuits to take care of that. So we discussed one model, the ideal model. Then we discussed another model that is called, piecewise linear model, meaning, okay, this is the current here increases all the way to IS. As soon as I put a reverse voltage, and I'm increasing this barrier potential, I'm helping the minority charges pass through, and this is sort of increasing linearly.
So,
Yes.
it's probably a dumb question, but so
There's no dumb
IS
question.
is the
Saturation
near-
current.
is the so that's when.
It's when the minority charges are drifting.
Okay,
Right? It's minority charges drifting. Why? So that's why it's limited, because it's due to the minority charges.
because there's always going to be some,
There will always be some, of
Some
course.
charge,
There will
because-
always be minority charges.
but it just depends on the intensity of that.
It will depend on how much is the value of the electric field that is pushing the minority charges on the p side and n side to the other side.
Oh, okay.
Right?
So IS is the smallest.
Yeah, it's a small, 10 to the minus 15, small, almost zero. But that's why, when I say it's almost zero, that's why I drew this one. That's why I drew this ideal characteristic. There's no IS, it's zero.
But current intensity depends on like the concentration of holes and electrons.
Yeah, that's the next stage. Next stage is now, okay, fine. Because the concentration of holes and electrons is different and it's actually exponential, which, I mean, the diffusion concentration, right? The concentration of the majority carriers. The majority carriers are the ones that give me diffusion, right? The diffusion, so since the concentration of the majority carriers is exponential, and they are the ones that create this diffusion current, hence the diffusion current is increasing exponentially, right? And that's why, okay, so first we went from, okay, if you went from the ideal model, okay, zero current in the reverse bias, infinite current in the forward bias, right? Then we said that there's another model where I have a fixed forward voltage. This fixed forward voltage, we set it at 0.7 volts. So we said that, okay, it's a piecewise linear model where I have a linear relationship in the reverse bias. So the saturation current increases in the reverse bias, let's say linearly, but it's a very small value. Then, in the forward bias region, I have a voltage beyond which current will increase significantly. Right? And that, we said, is around 0.7 volts, and that was, we called it the forward voltage. Right? And then we said that, okay, there's no such thing as such an abrupt change. It's because, change in current means changing concentration of charge carriers. Right? So since there's a change in current, since these charge carriers change their concentration, changes exponentially, this current is actually also supposed to be rising exponentially.
The 0.7, like, it's an example for a special, like,
0.7 is sort of the middle of this range that we have here. This range is about 0.5, let's say, to 0.9.
no, but like another circuit would have like 0.8, and it would, like, if it's more than 0.8.
Sure,
Okay.
exactly. Some devices will be 0.75, some devices will 0.8. Power diodes will be up to 1.2 volts even. Right? So, but for low voltage, low signal, low voltage electronics, it's between 0.5 and 0.9. That's the value that we should use here. But in general, it's a small window. Because why? Because it depends on this exponential will rise within a small window. Finish. I mean, it has a window for rising. At some point, fine. This exponential will go this way, but this you've increased the current 10 times as much as it was here, and the device will not even take that because its power dissipation will be exceeded. Right? So at some point, you exceed the power dissipation of the device. Right? Because you have a voltage and you have a current flowing. Voltage times current is power. Power is limited by the power dissipation. That's why they tell you it's always within a range, because it's limited by the power dissipation of the diode. Okay? So we have like three models now. Ideal, sort of piecewise linear with a forward voltage taken into consideration, and then the exponential. Okay?
But they are related to the reverse.
Yeah, of course. This is all reverse. This is all forward. So this is the forward characteristic of the device. And this is the reverse characteristic of the device. We will add stuff to the reverse characteristic. So this is the reverse characteristic, and this is the forward characteristic of the device. The forward is now done. I mean, we have a good handle of it. In the reverse, we will add a little bit more. It makes sense that if you keep adding a reverse voltage, meaning you increase the reverse voltage, meaning keep increasing this barrier voltage, what's going to happen? The barrier voltage was doing what? Was finding all the minority carriers and pushing them across the other side. If you keep increasing that voltage, it will be easier for the carriers, the current due to the minority carriers, to increase. At some point, you make it so easy that they travel right through the junction without any problems. They, express highway all the way through, and they actually start colliding with atoms on the other side, and they break their covalent bonds. Right? So at some point you do that, and then it causes breakdown here. So there's a zone here that will be useful zone that you can actually utilize. Okay. Beyond that, and that is called Zener operation. Zener operation of the diode, or we actually tailor that zone, and we create specific devices that like to operate within that region. Okay, and we call that Zener operation. And then this is called avalanche operation. Avalanche operation. So avalanche meaning, okay, you've made it so easy that they are walking past this junction, flying past the junction very fast because of the high value of electric field, colliding with atoms on the other side, breaking their covalent bonds, and this is just breaking more covalent bonds in an uncontrollable fashion. That's avalanche.
Wouldn't that be bad?
Yeah, it's bad. So we will not operate here. Avalanche means the device is breaking down, meaning you put too much reverse voltage. You put too much reverse voltage across the diode. But we like to operate here. There is a zone where you've put a little bit extra, negative reverse voltage across the diode, that it does something interesting. Okay, what is it doing interesting? If my device is doing this and my device is doing this here, let's say in the forward bias. Okay, and I'm measuring across my diode. This is my diode. This is my circuit here. What do I measure across the diode in the forward condition? When this is 1 volt, for example. What do I measure across the diode? Plus minus VD. What am I measuring across the diode? Come on.
Well, wouldn't it measure 1 divided by R?
No, it will measure 1 minus 0.7. Come on, 1 minus 0.7 divided by R.
Oh, okay.
Right? So, no, but that would be the current. That's the current flowing. But what will it measure here? It will measure 0.7 volts. Right? It will measure 0.7 volts. Is this going to change? It only changes within a small window as long as I maintain a certain value of current. Right? This gives me voltage regulation properties that are interesting. If I want to actually create a 0.7 volt power supply, right? How would you create this is a nice way to create a 0.7 volt power supply. Because, okay, how?
Specific.
What?
That's very specific.
But not very specific, because I can put multiples of those. And now I've created the what? 0.7, 0.7, 0.7, 0.7, 0.7 times 4. So I've created a 2.8 volt power supply.
Do people do that?
Yes, you can do that.
Oh.
You can do that. If let's say you don't care, because there's power loss associated with this, of course. Each one of these has a power loss. V forward.
And that's coming from a 1 volt power source, right?
In this case, it has to come from more, right? In this case, if I want to create a voltage regulator for 2.8 volts, here I have to put what? Something greater than 4 times 0.7. I have to put.
So that's how they regulate.
Yeah, I have to put. I can put maybe 4 volts here. I can put 4 volts and put a resistor here to limit the current through the circuit to a certain value that's less than the power dissipation of all of these devices. Remember, each of these devices will have a power dissipation equals 0.7 times I. So I have to choose I here so that I limit the power dissipation to a certain value that's in the data sheet. And at the same time, have them all forward biased. If I do that, then I can have here across this combination 2.8 volts.
I know, but 2.8
2.8 is it's a fixed value of voltage. It will not change.
Is that how people change the voltage inside a circuit by putting?
No. You want to regulate. It's a voltage regulator. Sometimes, let's say you have this AC voltage, right? This AC voltage. Do you see the lights flickering sometimes or no? Not these, not fluorescent lights, but the light, the incandescent lights. You will see them flickering sometimes at home, right? They're flickering. Why?
AC.
Because the voltage magnitude is not fixed. So if you are in a hospital, you'll probably not see that happening, because hospitals, fine, maybe the lights they will allow it to happen, but do you want that to happen in a cardiac support equipment? You don't want that to happen in a cardiac support equipment. So cardiac support equipment will be interfaced to the power supply using a voltage regulator.
Oh, yeah, so they add
You have to regulate the voltage. I mean, you have to regulate the voltage. I mean, you cannot have.
Is it something you attach?
Yeah, it's a box. You have to add this box in there to be able to regulate the voltage between this power supply and your load.
And that box is filled with diodes?
No. In the simplistic, the most simple way of
Oh,
doing
that's
it.
the most simple way.
That's the most simple way of creating a voltage regulator. Okay, I'm just giving.
There is like voltage regulator.
Of course, there is more sophisticated voltage regulators,
A bunch
right?
of diodes just put inside.
But if you don't care about efficiency, and you care about just getting a design out as soon as possible, or if you care about for a senior project, for example, for a senior project, create a power supply. Oh, I don't care. How am I going to do this? I don't want to create a complicated circuit, so I will do this. But there are other applications of diodes, right? We will see next class that there are other applications. This is just one simple.
By the way,
Huh?
you know,
Like everywhere?
What? Diodes are everywhere.
Like LEDs.
LEDs are diodes.
yeah.
LEDs are diodes. As soon as you forward bias it,
Do you know?
it will light up.
Yeah. So do you know how it changes color? There's three actually LEDs. One
Ah.
is red, one is green, one is blue.
Sure.
And the current that flows
Yeah.
determines the brightness.
Sure.
Wait,
So-
are those three colors inside one LED?
Yeah, just
And then
one
they
LED.
color
Yes, they
combine.
are
And
tricolor.
then they just
Oh,
use
that's
that.
cool.
That's very smart.
Yes.
I just googled it.
They're called tricolor LEDs. No, but not all. Because my friend used to make those large screens. You know the LED screens that
Yeah.
display stuff. So there are two ways to do it. There are LEDs that have three colors internally, physics by physics, right? Like
Yeah.
like you're.
Nice,
And
nice.
then what he was making is a cheaper kind. So they in every square centimeter,
Which
he
is a
would put
pixel.
he would put every pixel he would put RGB colors, red, green, and blue LEDs, red, green, and blue, and turn each one on with a certain intensity, so that you see at the end a certain scale of color.
Yeah, from a distance you won't notice, but when
Exactly.
you get closer,
No,
you can-
when you get close, of course, it's like pixelated.
yeah, exactly. But